So I'm going to talk about diffraction gratings. So far in the videos we've gone over single slit diffraction, double slit diffraction, and now in section 36.5 we're going to go over a diffraction grating, or basically diffraction through thousands of slits. Where you basically take something like, I don't know, you take a microscope slide, you paint it black, and then take a razor blade, and then just cut, hundreds of parallel lines inside that to make a diffraction aperture that's, many, many, many. So basically what we have is, we have just taken the double slit experiment and multiplied it by hundreds or thousands. So you have all these slits right here, which are all separated by the same distance, d. So the distance between each of these is going to be d. And then you have the waves coming in, this wave front that comes in, and then after that you just get wavelets all over the place, which then will start to interfere with each other. And so then what you get on the other side over here is going to be a diffraction pattern. So the idea is that the light coming from this slit projected traced over here, and then you find another one traced over here, and another one traced over here. And so if you have 1,000 slits, you now have 1,000 sources, which if they're all stacked up just right, are going to interfere constructively with each other. And so in the end, what you would have is a lot of interference to take into account. And so here I've drawn a much better picture of that, where you see the light. Now you see the diffraction, the slits are all separated by the same distance d, and then I've got light coming in from A and B and C and D. And so we could redo the derivation that we did for the double slit experiment, where we now have this right triangle between A and B, and a right triangle between A and C, and a right triangle all the way down to D. And so if each of these right triangles is a multiple of a wavelength with A, that extra distance is a multiple wavelength, then we're going to get total constructive interference with all of these different sources. So what is the effect then going to be on, what's the effect going to be? Well, if I model it this picture right here, so you can see with two sources, so I'm using the two squares, then I'm going to get the black line right here. But then if I now up the number of sources to 3, so you have 3 slits, and that's the triangles, then you're going to get the dashed blue lines, which you can kind of see are starting to get more and more narrow. The position of the maximum and the minimum stay the same, but all I'm doing is narrowing that the function, basically the spreading of the light in that bright band. If I now increase it to 4, so now I've got the 4 stars, these sources, that makes the much narrower red. So these bands are getting higher in intensity, more light is being constructively added to them, and they are getting much narrower. So that intensity now is being squeezed into a smaller space. So therefore the maxima keep the same location. So if this was the distance y along the vertical axis, the position of those maxima are the same. The space between them now, the dark band, the minimum, starts to get bigger and bigger, but essentially their midpoint stays the same as well. So really, we don't have to derive anything new. We've already derived it with double slit diffraction. And so what we have then is an equation that tells us that for the bright bands, the maxima, then d sine theta is equal to m lambda, where m is an integer 0, 1, 2, ... where m equals 0 is the central band, and m equal 1, m equal 2. So just drawing it one more time, double slit diffraction would give me a pattern of equal intensity here. So this is double slit, where I've got m equals 0, m equal 1, m equal 2, and on the other side, m equals 1, m equals 2. Now with the grading, I get the exact same pattern, but now I just get a line. Right here. So I can use the exact same equations that I had for double slit, for single slit, and it's still the same spacing between the slits. D is still the separation distance between slits. But now it's a lot easier to keep track of it. Instead of saying D we're talking about now is on, like, 10 to the minus 5, 10 to the minus 4. It's a really small number. So a lot of times what we'll write things is, if one line, one slit, is equal to, D, the distance between it, then the number of lines per meter, n, would be 1 over d. So one line per whatever the distance is. So a lot of times in diffraction gratings, they are given not by the slit separation, but by how many lines you can put inside of, say, a centimeter, or a millimeter. How many, whatever unit is most convenient. Okay, so the interesting thing now is that, and this leads us to section 36.6, and that is what we call dispersion and resolving power. So now if I put white light through, since the diffraction equation, the separation times sine theta is equal to m lambda, since it's wavelength dependent, then if I put white light through a combination of many colors of light, what I would see, and what you probably saw in the laboratory, was I get a central band, m equals 0, but then at m equals 1, I would see, I'll put an m equal 1 on both sides, and then I'll even go to m equal 2. What you would see is you would see a red line at each of these, m equals 1, m equals 2. Then you would see a green line, and then you would see maybe a blue line. So the colors would disperse. They would spread out that's why the diffraction grading is such a key thing for something like spectroscopy, where you're trying to actually figure out what the wavelengths are of the light. And so now you can measure the position of the red, position of the blue, position of the green. You can measure the angle theta. If you have known distance between the slits D, then you can measure the wavelength. And you can do it actually multiple times. You can do it with m equal 2, m equal 1. Maybe if you can get m equal 3 on the spectrometer, that would be good. So to try and calculate how these different colored wavelengths are dispersed, so the dispersion is D. We can think of it as how far we're spreading them out, d theta, for how much with the difference in the wavelengths. So, we're measuring, say, in this case, delta theta, and we can measure that between a wavelength of red and a wavelength of green. Then we can do it over on this side and see what's the dispersion. How is the red and the green separating in our diffraction experiment? So for the grading, yeah, we can just basically look at that. We can look at the separation in the angular separation per the difference in the wavelength that you see. Now, the other thing, and maybe another useful quantity to describe this separation, is the resolving power, where this time we're, say, given an m, so we're saying we'll pick one, m equals 1, m equals 2. How we're going to resolve those different colors is if we take an average of the wavelengths of, say, those two colors, and then we look at the difference in their wavelength. So basically we're trying to figure out, given a specific diffraction grading, are you going to be able to separate the green line from the blue line, the green line from the red line, or are all of those lines just going to blend together and give you a nice rainbow color? Or would you like to see nice, sharp peaks separated from each other? So basically, if you look, what we're looking at, the resolving power is you're looking at the, the average wavelength, how well you're going to separate red from green or red from blue. Because if I have a diffraction grading that's not very good, then the reds are going to mix with the blues, the reds are going to mix with the greens. You'll get kind of a washed out rainbow color instead of nice, really sharp, narrow lines for the different colors. Okay, yeah. So in the end, so we're calculating is the average wavelength. So it's the mean of two color lines for a given m, and then delta lambda is just, lambda of one wavelength minus lambda of the other wavelength. Now what we could do is you could work through the derivation and find that this resolving power can also be calculated from the number of lines per meter, the number of lines in the grading, times the specific m value that you're using. So m equals 2 is going to separate those colors a lot more than, say, m equals 1. If you can really swing the spectrometer arm to a large angle, then you're going to spread out the reds from the blues and the greens over at m equal 2 more than you would at m equal 1. Of course, the problem then is the intensity drops when you go to larger m, but you can also maybe separate those much better. So it's a trade-off when trying to design one of these spectroscopy experiments.